Welcome all to the lecture. Let me just quickly open. Um, yes. So welcome all. Let me open this one. Um, yes. Eh, so today I see people have not joined today, and that's okay. So today I think we are in the sixth lecture of sixth session of our series. Okay, just let me open this up. I think this is the one. No, is this the one? Yes. Okay. Hmm. Right. So we are in our sixth. Today is the sixth session of our live interaction session. For the last 5 weeks, we have been focusing on looking at applying numerical method. That is it. This is what the course is about. Let me also open up the first notebook that I shared. Um, yep, this one. Why doesn't show images? Okay, that is weird. Please let me open it this way then. Okay, so so definitely it's session six. I'm Shrey Sahai Gupta. Uh, just a quick introduction. Most of you would know me by now. I'm a PhD student at IISc Bangalore. I'm in my fifth year of PhD, and I'm the PMRF TA for this course, taking live interaction sessions. So I invite you guys to bring any doubts or something that you have, and we can discuss those. Let me quickly go to before I get on, continue our discussion from last two um, last session. We had left things off to the last week. So let me finish that and then inter revise the entire thing, and then let's get going with this whatever I have thought of discussing in this week's session. So where were we last time? Let me open uh let me open this PDF I had. Also not PDF, PPT. Where is this PPT now? Even materials. It's not there. Interesting. That's not good. Let me see. So wait a second. Oh, it must be there. Not in notebooks. Okay. Please excuse me. My laptop seems to not be able to mm, handle. It's kind of hangs when I. Okay. So it's back, it seems. Okay. So let me bring what this PPT and the discussion we have had last time. We also had this script that I was following. Uh, Let me open that as well. So essentially, let me go through the matter at hand. So essentially, we were somewhere at this point. We had understood the basics of finite element methods, and there we wanted to now further explore. Uh, so we understood the numerical methods. Now we wanted to apply it, see how it applies numerically. So let me also open up this, yeah, these set of equations. We have two primary equations there. Mm, Yeah, so you can actually take the summation sign out. We were somewhere here. So we were looking at minimizing this integral, which people would like to call as uh, this principle of least actions and variation. You basically want to reduce the residual, and from there we got this equation, and this is where we are. Now, certain substitutions like these into the above equation and then setting it up to zero. This is what we want, gives us this equation. Uh, so let me write this equation like this. Let me remove this part of it. Let me now, basically what we're doing is from this point, we now need to go to that AX equals to B kind of situation. And that we have to do by hand calculation. So let me do that. Uh, See, we have theta phi here. Yep. So, so we have phi here, and we need certain expressions to to move forward with this. So actually, the notations are actually indeed not consistent. So let me make that correct that. This should be this one. Okay. One more thing is, yeah, that everything else is okay. Okay. So now we know this, we need to figure this one out. Okay. Okay. So definitely, so this is a hat function. Let's first realize this, that how does this look like? So suppose there is this node I. This is the ith node. Okay, and this is on the domain uh, like this. Okay, and there will be uh, neighboring nodes. So let me do this. Right. So now let me just label them. This is the ith node. Okay. This will be the I minus 1th element. And let me just say this ith element. So what is going on there is this is the ith element there. Now this hat function looks something like this. 1D, and come on, this one, yeah, where if I also draw the value axis or the y-axis, if I draw the value axis somewhere here. So hi Apurv, how are you?
Yes, sir. Fine, sir. Thank you. Good evening.
You joined, right?
Yes, sir.
Can you hear me? Is the setup okay? Great. No doubts this time.
Sorry, sir.
Any doubts? Any doubt you have from
No, sir. It's fine, sir.
it? Okay, fine. We'll move ahead. So then this one is 1 and this one goes to 0. So these are, let me also mark what is this. This is phi I of x. Okay, this is how it looks like. It looks like a hat. And now phi I of x. Uh, we want gradients of it. So let me also put this thing up and use this only. You know, it's 0 otherwise, but in these two cases, it simply is 1 by delta x and minus 1 by delta x. Okay, this is there. Um, Fine. One more thing is this integration. We need to look at this as well. How does this integration follows? Um, Basically, um, just give me a second. The computer keeps hanging. It's not a good sign.
Excuse me, sir. Sir, you are muted.
Let me stop sharing for a second. Reshare. Am I audible now?
Yes, sir.
Okay, so I was saying this computer of mine keeps hanging. That's the issue. But essentially, what I was discussing, meanwhile, my computer was stuck, was that this integration is something that we'll do manually in this in this session. But this is something that a finite element code will have to deal with for a general purpose application, that this integration has to be solved dynamically. Upon changing problems, this has to be done uh, depending like this integration has to be done irrespective of what the function is. Here we are going to do it analytically. So if you were able to hear me, I said that this can be done using something that you have already covered in this course, which is new, or maybe covering this week. I guess you're covering it in this week, which is numerical integration. So this can be done using numerical integration also, but here, just for the sake of demonstration, we will go ahead and look at it this way. So if I do it uh, this way, I need to integrate this thing, right? So this integration is what? What can this be written? This can be written as xi minus 1 Okay, and then also this part. I know this is a little bit tedious because you guys have to wait and keep seeing me keep waiting for me to write the entire thing, and then, but what to do? That's the problem there. And we can go ahead and start putting in equations also there. So one thing to note is that 1 by delta x can be taken out. So that is something that we can do upright now. So this is 1 by delta x, and then can be taken common, and then we can put these equations there. So this can put as, let me also write it as x. There's a lot of inconsistency here with the way I have uh, in between lines of these mathematical equations. But anyways, becomes a little confusing. Let's go ahead. So this one will become e to the power x, and then you have x minus xi, right? And similarly, we'll have x I minus x. Let me see. Yeah, this should be xi plus 1. This should be xi minus 1. Yeah. Maybe a change of variable is also something that we can look at. This is e to the power x, and this is also. Maybe we can look at a change of variables at this point. So let us do that derivation. Okay. So if I do this, what essentially I have is We can write it as y, where y will go from 0 to delta x. Okay. And this e to the power x has to be written as e to the power x I minus 1 and e to the power y, and this range y equals to x1. So basically dx equals to dy. Yes. So what is y? Y is x minus x I minus 1, and similarly we can also write this as okay. Let me write this as z, and this will become e to the power z as e to the power minus z and e to the power xi plus 1 e to the power z. By now you must have guessed what z is. Pretty straightforward. Okay, so with this, yeah, we can take few things out also. What do we know? We know that exi plus 1 is exi minus 1 uh, plus 2 delta x. And so from this we can take this thing common to take this out. Let me take this out. What else? E to the power, yeah, this e to the power 2 delta x can also be, I'll rather take this one out as well. This integral. Okay. And now we need to integrate this thing. So again, applying integration by parts at this point, this will become, this entire term will become what? You integrate, you keep y there and integrate e to the power y to get same term. You get this starts at 0 and this one is again delta x. And we have minus double integration of e to the power y. So y gets differentiated and e to the power y integrated as e to the power y, and then again e to the power y integrated as e to the power y. But this time we get a limit there. Uh, so just I'll remove this part. And similar stuff, but a little bit of caution, because this is e to the power minus z and not the same thing. So let me use some other sort of brackets here. Let me put z and e to the power minus z. So every time we integrate, there is going to be a minus sign that is going to pop up. Because this integration is going to happen twice in this case, there will be no minus sign here. So this minus and this minus can be actually taken out to give you this term. And yeah, actually there's a mistake that I have done. This should be Z is, yeah, this should be 0. This is the mistake that I have done. Control. This should be 0 and this should be delta x. Couldn't ensure that. So this is how it is. Now this is 0. This is delta x. And this is 0. Is this okay? I think, yeah, looks fine to me right now. Now let's open this entire thing up also. See what do we get. So here we will get delta x e to the power delta x and 0 into e to the power 0. So basically, uh, delta x. Then in this case, you're going to get e to the power delta x. You remove this part and then you open up here. So this has to be z. Wait, this to be z. Consistency. Okay. Now when this bracket is opened up, we write a minus sign delta x e to the power minus delta x. This is okay or not? Yeah, this seems to be okay. So minus e to the power delta x, and this one again you will get plus. Note there is a plus there, e to the power minus, and there are also ones that are going to be there. No, here also there will be a one. Miss that part. Minus minus plus 1. So e to the power 0 is 1. And so here you get minus, you get 1 minus e to the power delta x. I suppose this is a little bit clear because it's basic. You could have done it by on your own. But anyways, this is the minus sign there. Now I'll take this e to the power 2 delta x inside so that we can get this e to the power delta x common amongst things, and this minus sign can also be actually, this bracketed term can be actually opened up. Once this is opened up, what you get is plus, this one gets minus, this one gets plus, so these one gets cancelled. So there is a lot of cancellation that is going on here. Yeah, only these two terms will stay. So essentially I can actually remove this 2 e to the power x. This delta will also go. So this x I minus 1 plus delta x. This does not seem correct. Let me check. I made a mistake somewhere. This does not seem correct. Essentially, what I'm getting is 2 e to the power x, isn't it? I'm not sure of this result. Let me check once. Again, referring to that paper. So can you cross check? Is Apur there now? No, he's not there. Anyways, so nobody to cross check this. Right, let me check it up. Okay, let's believe that our derivation is fine. No. See, in the limit, actually, one more way, let me try this. One more simpler way would have been to, because we have e to the power x here, we could have gone further and did do integration by parts in the first place only. Hmm. I'm using these two interchangeably, so ignore that part. This should be 5j, and you integrate e to the power x once, then you get minus. You differentiate this term, and there's an integration term that has to come. This is 5j dash e to the power x kind of situation. Um, no matter what phi j at 0 and 1, this one cancels out, so this one goes to 0. What we are left with is this term. And now we can break it up using this. Where I 8. We can actually take this thing common only. Let me take this thing common. In this part of it, it is simply e to the power x dx. In this part, it's minus e to the power x dx. That's the easiest way to solve this integration as of now. Okay, so now one last step to see what is going on here. This becomes okay, one more thing. Just copy pasting this entire thing. What's came? So what do we get here? We get e to the power x minus xi minus e to the power x I minus 1. What's wrong? Something wrong there. No. And then there's a minus sign there. So e to the power of x I plus 1, and you get plus e to the power xi. Okay. Okay. So what essentially we have here is we can take e to the power xi minus 1 common. Let's do that. Let me take this and put it here. Let me take e to the power xi common so that we get this kind of term. Let me check if this is the expression that we were supposed to get. E to the power xi minus. So see this term resembles this one better, right? And this up. So many. E to the power x. Just give me a second. This one is, yeah, right. I think this is the correct term. Whatever we did there is something on the wrong. Let me check. This one's fine. This one we had said e to the power minus z integrated comes, this gets a minus sign. This one should be minus, I guess. Let me think. So there is a minus sign because of this one. What minus sign is this? This is because of integration of e to the power minus z. On this term, e to the power minus z gets integrated twice, so that's its contribution gets cancelled. But it already has a minus sign there. So this should be minus. Now if that is there, okay, then minus 1, okay. So this one will become plus minus e to the power. Now if that happens, then the entire thing changes. So this one, some weird uh, like cancellation happened, which I realize. So first of all, we can take e to the power delta x common here, that this becomes e to the power x. Or let me take this inside only, so that we have 1. Now this one will become e to the power xi. Okay. This one will also become e to the power xi. This one will become e to the power x I minus 1. This one will become e to the power xi minus delta, isn't it? Even here I've done it incorrectly. This should be delta x minus e to the power delta x. And then 0 is that's okay. So here, when we multiply, let's forget this integration for time being. We're running out of time also. I think this one is okay. This is what we get. Okay. This integration is there. Let's come back. Some weird stuff I have done there, which we can just simply ignore. A simpler, more clear integration procedure is fine in the interest of time. Let's move ahead. So we know this integration, this RHS we know, right? Let me just see what, yeah. So one more thing is, uh, now what about this LHS? So let's look at that also. What do we do of this LHS? So this LHS is quite tricky. Well, not tricky per se. So there are three cases that can happen. What can happen when there are three cases that can happen? Let's look at this kind of picture that we had drawn. Okay, so this is one case. Let me I'll do is please. What I'll do is I'll put a hat only. Okay. and I'll put a color around it, an outline. Let's look at a color kind of situation. Let's increase the transparency. Okay, what can happen? Um, there can be these three cases, or like, let me see how many cases there can be. Okay, put hmm, okay. Let's change the color of this to yellow. There can be this situation. Okay, there can be this situation, and there can be this situation. And let me also one more situation, which is this. So there are only four situations are possible, right? Are there any more like any other orientation possible? I don't think so. What is this case? This is I equals to j. Okay, because this is the ith node, there will be a jth node corresponding to this one, right? What are these two cases? When this is the case where I is j minus 1. This is the case where I is j plus 1. And this is the case where otherwise, right? Okay, come on, x. Okay, now note how there is an integration associated with this integral. Sorry, there is a summation associated with this integral. So for any um, j, for a given j, there are all kinds of I values that will happen. So we know that this I is gonna traverse over the entire I values, or over the entire range of I's, and there will be these three cases. There are these three cases that we need to take care of when evaluating this integral. Uh, okay, so okay, so what happens when in this case? What do you write? This in this case is 1, right? This is simply 1 by delta x square. Okay, here there is going to be a opposite signs even in this case, and there in otherwise it's 0. Okay, and when that's minus, when I'm saying minus and minus, we know for I values which are either j plus 1 or j minus 1, this integration is going to be in the common region. So that we have to take care of. So this, let me um, shift this and write the contributions to this integral. Okay, contributions to this integral. So actually, that only the this thing will change. Definitely, you will get this, and the only region is region of delta x, right? So this is the only contribution that you're going to get is It's actually for a given j, we're traversing from j. So we are traversing from actually now I need to define, but does not matter so much, right? Essentially, you now know that the contribution is just going to be -1 by del square. One more thing. One more thing. Let me check. This integration happens over all I values for different j. So j is the equation number. I there's an integration over I. So I is moving. So when I equals to j, this is okay. When I equals to j plus 1, I equals to j minus 1, let me say. And this is I equals to j plus 1. So in this case, this integration is going to happen in which region? X j minus 1 to xj, and this is xj to xj plus 1. Actually I have to yeah, see this integration. Actually it is not correct to I don't know if it is correct or not. But think about it. I'm thinking this one is definitely correct, right? So the contribution here you can write 2 times 2 divided by delta x yes. So this takes care for only that I value, which I equals to j. For I equals to j minus 1, you get -1 by delta x term. And you have to write plus also. We write plus. Then we go ahead and write plus and write this is for this -1 by delta x plus 0. Okay. Now important thing is you have to multiply ai's to all values, so that we have to put this will be ajj will be a j, the jth equation, the coefficient for j minus 1th, so this is j minus 1th coefficient because we are substituting for I. So a j minus I, that's it, right? And then this is a j plus 1 and 0. So essentially now we have our equation. Now this is quite clear. We are already there. So now we know there is a system of equations to solve for, where we are essentially writing that AJJ um, 2 divided by delta x plus minus 1 divided by delta x a mm, aj minus 1 plus minus 1 by delta x a j plus 1 is equals to, it is equals to what? We have found out that term. It's equal to this minus of this. Note how there is a minus sign there. So we substitute that plus, oh, plus and then minus 2. Okay, we can go ahead and absorb this value to put exi plus 1 and exi minus 1. Okay. Now the way you write, so again you can see this is a tridiagonal matrix, like how we had discussed, and now it becomes a simple solution. So let us do this part also. Mm, okay, so I'll keep this intact and I'll create the library for today, which is 2nd September, right? So today we are essentially gonna finish our understanding finite methods, something that you're going to briefly overview in the next 2-3 weeks, and then we're going to move towards a more mm, general this thing hanging. So I prepared now. So basically we'll move towards regression, optimization and stuff. And to bridge this from bridge the transition from these finite element methods to ODEs, we'll see a little bit of numerical linear algebra, specifically singular value decomposition, a little bit of its application and so on. So let my computer respond and then we'll begin. taking time. Let's see if it has responded or not. Everything is okay. Still not responding, huh? Okay, finally. So again, I'll just 2nd September 2025. Let's discuss this part. We'll just quickly take these things. I have the code ready mostly, but for the finite element, first of all, we'll define the number of elements, let's say 5 or let's say 10. We'll have the del x term. You see, del x is going to be used a lot. Then we'll also use this thing, locations of x. So 0, 1, and then nodes. Note that there are n plus 1 nodes similar to finite element. Now A will be np dot zeros because we have we have not dealt with boundary conditions up till now, right? Let me see. Deal with boundary conditions. I have not dealt with that. I also have to see how boundary conditions are dealt with. Or no. Yeah. So boundary conditions have to be dealt with by saying A1 is 0 and AN is 1. So that is something that you'll have to see. It has gone very slow. Let me stop sharing let me wait for it to respond. I think it's taking too much memory right now. That's why. Yeah, it has started to respond. Yes. Okay. Then B also will define. Eta 0 is 0. Eta of 1 is 1. What else? Okay. Theta. Or let me say A right now. A is np dot zeros n plus 1. Okay. Now we come on here, start responding. Let me stop sharing. fully irresponsive it has gone. I don't know if I open my camera, what will happen. Should I just go ahead and see? Hmm. Let's see. Not responding. Why is it not responding? Let's check. Good place to be. Come on. Ah, started responding. Okay. Okay. So now you have to just quickly put this thing. Um, we'll define invert of del x. We could have done that up there. Now the boundary condition says that if I equals to 0 or I equals to n, then kii is 1, else if I is greater than 0, then ki I minus 1 is invert del x. Don't need this. Then invert del x. Uh, just minus invert del x. And so is the case with ki plus 1. Kii on the other hand has to be 2 invert del x into 2. At the same time, we can also substitute fi to be invert del x 2 and p dot exp xi plus 1 plus np dot exp xi minus 1 minus 2 into np dot exp x. Here you put if I equals to 0, fi equals to 0, else fi equals to 1. This is for the boundary conditions. Okay, else we need to do nothing else. That's it. This is the finite element code. Now, once we find ourselves, what is k? Oh, I've used this different notations. It should work. Now we have AIs. So now, first of all, you guys need to realize that now we have functions rather than point variables. So we can't just simply plot it. We need to first establish functions. So first of all, write definition shape function shape I, so that shape, and you say x comma I. So there, if you write if x is greater than equal to xi minus 1 and x is less than equal to xi plus 1, only then you return okay, then you return x minus xi minus 1 divided by del x Okay, there is no del x here, so inverted del x. Else if you have x greater than xi and x less than equal to xi plus 1, return xi plus 1 minus x into inverted del x, else you return 0. Theta or theta only is np dot zeros. Input at some, let's say, x test, np dot 0, np dot length space at 10, let's say at 100 points, you would do it at the end of x test. Okay, now you write theta equals to so for I range A, len of A, so that you get AI is AI, and then you write theta. As I told you, theta is a function of x, right? Theta is equals to, so theta has to be 0, right? At all locations, theta will have to be theta plus AI. Let me put it AI like this. And then you say np dot array phi I xi comma I for xi in x test. Okay, so this is the code there. Now this is shape. Okay, works fine. Let's plot this thing. I've taken this code again. We had this. So one important thing which I'm missing is what? Okay, this one. See, this signature is not right. that I had to correct. Let's see. Checked it properly. Okay, let's see. Should be minus. Oops. It matches the exact solution, and there is a difference at low discretization. It's just one important thing. This has to be. So important stuff is this minus sign and that minus sign will get cancelled actually. This has to be actually negative. That's what we have not done it properly. That's why this shows that. Anyways, I think this is okay. This is what you get. And if you start increasing the discretization, you will get finer and finer values. The important part here is that at the very nodes, the solution is very correct, which was not the case. So the error is zero, exactly zero at the nodal points. That is an important part of um, finite element. So finite element, thetas are exactly zero. That's how it is defined, which is a very strong point that at least the way you have done it at the very nodal points, you're getting very exact values. Error is zero there. Now, so those are some advantages of finite difference, finite element, and this kind of sums up our discussion there. So let me close um, this one. I'll try to put it up. I'll put it up, not try to, I'll put it up. This I'll leave. I'll close this also. So essentially, what we have, let me, now let's talk what's next. Okay. So the way we moved, this is the wrong one. The course overview now asks us to discuss something on linear algebra. That is what we need to do now. Okay. And just like last time, when a question came about TDMA, or maybe last time, tridiagonal matrix, another thing. The essential part is, or essential reality is that these algorithms are well established. We might be interested into knowing how they work, but I think it is more beneficial to be able to apply them, and this is where we would like to work on. Now, TDM and everything is okay. but those are not the most popular numerical schemes in linear algebra. That uh, title is, I must say, uh, held by a very prominent algorithm, which is called singular value decomposition. Might be an advanced topic at this point of time, but it is nice to see how a real world, as it's also a well established thing, but it finds a lot of applications, especially in machine learning, regression, data analysis kind of stuff. And the underlying theory is also profound. So maybe we'll have some discussion on singular value decompositions from now on. While my laptop uh, stops hanging, let me take a quick break and come back. Okay, let me quickly take a break. So today we are going to do a little bit on SVD, singular value decomposition, and what it does. Okay. Um, okay, let's see how the next half an hour goes. I'll try to introduce it to you and start fresh from the next time, especially given my condition of my laptop right now. But definitely we'll see a little bit of introduction to SVDs. Okay, I'm a little back. Let's talk about this thing. What is singular value decomposition? How do I begin? This is a profound topic in linear algebra, which deals with what? Linear algebra deals um, with tensors, matrices, matrices being a very general one. And an interesting part, let's look at a good application of linear algebra. Okay, so this is a code for image compression. This is one of the ways images can be compressed, and we'll see that in action today with a simple few lines of code. Mark that this entire code is written by AI, ChatGPT. It is just that the principles of it we are going to understand. So what I have done is I have taken an image um, and tried to compress it. And depending upon a parameter that we decide, we will see results. Okay, let's look at 4 image compressions with parameters 1, 5, 25, and 125. Let's see what happens. Tried running this code now. Let's see if it's running. Yeah, so it ran. ran with 25 and last one is 125. Let's wait for it. Yes, and there are some results. The first thing is there is this singular value log scale for red channel. We'll understand this part of it later on. But what we see is that there is a singular value index. And the last value is around 850, I guess. 852. There are 852 singular values for the red channel. We'll talk about what red channel is, what all this is. But let's look at the fancy stuff. This is the image that I was um, interested in. Let me tightly out this. Okay, look at how clear this image is. Okay, with a very sharp kind of very stupid, let's not say stupid, but this is the most important information. Let me say this frame stores the most important information uh, of this image, and you can actually recognize that. So this you kind of see that there is some darker object in this part of the image, and then whitish kind of figures there. But if even if we first just and k, so k is actually the number of important variables that important values that we will, let's say eigenvalues for loosely speaking, let's say this image is somehow related. This image also has a eigenvalue kind of concept. If we try to construct this image using the only one most important eigenvalue, then this is how the image would look like. But if we want to do it using fi- five most important five most important five most important eigenvalues, we are the image is able to we are able to represent something, some weird thing. We see that there is a dark object with two tiny things going on, and you see the colors are also not exact. But if you increase it to 25, now we can see that at least in principle, this image is quite, these two are quite same. For 125, it might be hard for us to realize that these two images are different. And this might be something where this might be a region where we must be looking for um, image compression. So this image, as you see, there was an index of 850 elements. There were 850 kind of eigenvalues. What we were saying is singular values of this image, and only 125 were able to figure this one out. So let me redo this. Okay, before I redo this, see the compression ratio which different k values give. The image is compressed to 500 times with only one value. Okay, and you can kind of guess that because 850, it's not exactly matching, but it is in the same order. So 850 values, but we have taken only the first one value. Okay. For k equals to 5, you see 850 by 5 is what? 850 by 5 is 60 something. 160, 850, no? 160 and 25. Yeah, 160 and 25 is 185. Sorry, 170. Wait. Yeah, so 170. Yes. So now 170, and then you're getting on the same order of compression ratio. If with 25, 850 divided by 25 is another order of magnitude, so 34. Compression ratio is around 20. With 125, the compression ratio goes to around 4 or 5. But 4 or 5 itself is a big number. So to represent the same number, you have just reduced the size by 4 times. So it's only 25% of the total image. Okay. So this is an application of singular value decomposition. And there are key concepts with this example of understanding how this apparent algorithm, which I have brought without properly explaining what is going on, what is this algorithm about, we can actually realize that we're kind of trying to represent an image uh, or any data, let's say any data, with lesser number of values, isn't it? And that is why this is something exactly what SVD does. SVD dimensional, it reduces dimensions. It is used in reduced order models. It is used in dimensional analysis. One more important thing which I wanted to point out is the relative magnitude of different singular values. You see, the first value has the most importance. It stores the most importance. But the other images relatively have much lower. Let's look at the first five values, okay? Or let's say first 10 images. You see, once you have gone to second, 1, 2, 3, 4, 5, you see, let me do this. You see now, the next few eigenvalues are quite in the same range, right? They change order of magnitudes by, let's say, in this kind of situation. Then we see that it's a more or less linear only. Okay, so let's look at this kind of region. I'll see 1, 2, 3, and then 70. Okay, 1, 2, 3, and 70. Let's look at what is going on there. This is something on data deduction. We'll see how this is helpful for us, or how this is a numerical technique, something called as principal component analysis, or this comes in handy in regression. And there's also an angle of matrices and linear algebra in this algorithm. We'll look into it in the next session or something. I'm just trying to give an overview today because there is not much time now. And I'll tell you an important aspect of this kind of piece of code. This piece of code actually is removing redundancies also. You actually, by just looking at these images that are being generated, you should also appreciate that certain images are less redundant than others. So let's talk about that. The k equals to 17 gives more or less the same uh, image. We know that we can see that there is a little bit of fine tuning or whatever. This is something, but you see from k1, see k equals to 1, there is nothing. We know the background is blue at least. There is some reddish kind of stuff in between. Okay. There is a little bit of white, there is a little bit of red, little bit of brown, and there is a little bit of blue also, dark blue also. K equals to 1 is able to give you that much information. So major colors of a image. K equals to 2 directly gives you an object also. It recognizes your object also. You see that? It realizes your object. And do you, just by looking at this, do you realize how AI in principle is able to identify objects? If you think about it, if I were a AI model, I would do this and only focus here in this part of it and mark that this is an object, right? This branch does not enter k equals to 3 or something, but k equals to 2 is interesting. Okay. Now let me do with 2, 10, 2, 10, and 51s. Let's see one last time. So you realize that this is kind of also removing redundancies as far as some application is involved. Say object identification. If you want to locate an object in an image, this this algorithm is a good algorithm, right? So this has a numerical application, not directly in numerical methods per se, but it is a profound numerical technique in linear algebra, and we'll discuss that it more in our future sessions. Let me quickly show this to you. Yeah. So see, k equals to 10 itself is not a bad, uh, what do you say, bad reduction. If our object is not for aesthetic purposes, even k equals to 50 is also able to give you a good kind of things. So you see that branch, the information of branch is somewhat stored in the next 40 elements. Okay. So just to identify that there is a branch and there is a bird, you don't need k equals to 70 also. Just k equals to 50 is also fine. Maybe even lower values also we could, like, we are, at least with our experience in AI, we know that to identify if there is a bird in that image or not, our AI model does not need the entire image. The only first 50 values, singular values of this image are enough to identify that. At least if that is our application. Okay. So we know that in some sort of there is an information reduction or information extraction kind of stuff going on here. Okay. Uh, this becomes most important and very interesting, where this will find very good application where there is a lot of redundancy. Okay, so let me put 2 and 10. 1 also I want to put. 50 I'll remove. Now I've changed the image to Indian flag. Okay, okay. Let's look at how Indian flag looks like. So even k equals to 1 gives me the 3 major colors, and we know there is a little bit of blue in the center, but they're not that clear. K equals to 10. The first 10 images are enough for us to identify that there is a reduction. So you see that there is a lot of redundancy per se. There are patches, there is a pattern there. These patterns that we don't need this image for us to store this image, or let's say for us to, when we say store the image, we are kind of saying that we want to retrieve the same image with the same quality and stuff. But if that is not our application, if we want to just store a copy of this image for some application, let's say we want to store this image in as small as size as possible, this k equals to 10 is enough. Let's see how much kind of roughly how, see, oh, it is very interesting. See, this whole singular values, this image has roughly 400 singular values. But then in the first 120 cases, your entire image is captured, first of all. This is an interesting case because there's a pattern there. And even there, you don't need much. The first 10 images are also enough, as we saw here, right? So that is also important. We kind of see there are fine tunings going on inside for the next 60 elements. Okay. One last thing. This will not work for which case? I want to, when there is a lot of fine tuning or fine features in an image, then this will not work. I wanted to show that to you. So let me take and see how this one behaves. Even I have not explored this part. So let's see. Okay. Quite fast. This one, because it was a single value. Actually, this is the black and white. So this one gives very nicely. See, the original image, you see there's a black object in the first two singular values, singular values. You are able to identify the object. The next 10, you're able to identify fine features near this main object. You see, right? Um, Similar to how the last time fine feature thing, this one also has very large fine features. So I don't think much can be done there. But we know that there are singular values which are order of magnitudes larger than others. Okay. Uh, Singular values are much lower now in this case. So let's also 70 is actually at a good par value. You're able to capture a lot of features there, which is very interesting. Nice. So this is something there. If there are even further fine features, the entire image was filled with fine features, then this would have been nice. Again, it got hanged, my laptop. So maybe at this point we can stop only. What do you think? Mm, Yeah, maybe we'll stop. Maybe we'll play around with other images in the next time. So I'll try to log out now. Okay. So see you next time.